I have to admit, I'm a little nervous today, and I normally don't get nervous at giving talks. And there are two reasons I'm nervous, and one is my wife is here. And she's been here with me for 24 years, every step of the way. I love her deeply, and she's always had my back, and I really want to do a good job for her. And the other reason I'm nervous is my colleagues are here from the Department of Psychological Science, and this has been just a tremendous department. Not only is it an incredible collection of talented and smart and exciting and generous researchers and colleagues, we also have a really good departmental culture. And we have a really wonderful history. And so I'm really, honored and humbled to be part of the Department of Psychological Sciences. It's a wonderful place to be an academic. All right. I just want to start out with my collaborators on this project because my collaborators, basically, a lot of the work is theirs. They do lots of stuff. This picture over here, let me get out my laser pointer, is Jory Province. It kind of works. A former student. This is Richard Morey. Richard was also in my lab, but now he's a professor at Cardiff in England. You've met Paul. Paul's been tolerating me, coming over there anytime I want, knocking on the door, interrupting, and asking him questions. I've been like the biggest pain in the ass undergrad he's had for 16 years. This is E.J. Wagenmakers. He's a colleague of mine at the Netherlands in Amsterdam, and for a while we were like competitors. We were both kind of racing for the same ideas, and we realized we could slow down if we just worked together. And this is Dong-Chu Sun. He's the chair at Stats. He's not here. I'll be sure to remind him of that. He's also been a colleague with Paul over the years and tolerating my questions as well. All right, let's move on here. I have this. I want to start with the Heisenberg uncertainty principle, which might seem like a strange place. I just wanted to use it as a prelude. The Heisenberg uncertainty principle states that one can't know the position and the velocity of a particle to arbitrary position. There's always a little bit of give. When you put the photon on the particle to learn about it, you change it a little bit, all right? Now, when I first heard about this, I was in 7th grade, and I absolutely hated it, right? I'm sitting there in a white suburban male. I have all the privilege in the world. I had no need for such limits in my life, right? I wanted to know. I could not believe this was the case, right? Clearly there was a mistake. There must be some better way. Certainly we could learn this, right? I want to hold this in mind because I think there are some real strong limits on what we can learn in the statistical realm that maybe we're not respecting as much as we should. So I just want to use this by analogy. I think people have like the same my little 7th grade response of surely we can do this. Well, there may be some fundamental limits. All right. When I first got here, our department was the Department of Psychology. Now it's the Department of Psychological Sciences, all right? And this reflects a field-wide trend. One of the things psychology wants to make clear as an academic discipline is that we are a science. We use the scientific method, we run experiments, we got statistics, we consider alternatives, we control things. We're science, all right? And maybe if we make ourselves the Department of Psychological Science, we'll get more money. All right. But I would argue that there are some recent bumps in the road in the literature, all right? So let's just call them bumps in the road. I'm going to talk about shaky claims. I'm going to talk about replication, and I'm going to talk about fraud as being some bumps in the road of being a science. So, shaky claims. It starts with BEM for me. This was kind of a godsend for me, actually, for Bayesian statistics. Darrell Bem published an article in the Journal of Personality and Social Psychology, arguably the most prestigious journal in social psychology for sure, maybe across psychology, where he talked about or made the case for ESP, the notion that people would feel the future much like you feel something as being hot or cold. It's literally at that level. And the idea was if the experiment was set up right, people were able to avoid potential costs and find potential rewards, choose them even though they could not know which would be which by any other method, all right? And this was a beautifully written article. It did everything right. You read this and it's just exactly the way an article should be written, except for the ESP part. And, Fox picked it up, and all the outlets picked it up. It was a great feeding in the New York Times. And so here's Daryl Bem with Stephen Colbert saying, I feel what you're going to say. All right. Literally, people were able to predict what the computer would generate later on. That's the claim. Here's another one that's kind of modern. This one's about thinking outside the box. Literally, if you have an avatar and they're inside a squared-in area, you're more creative. But if your avatar is outside a squared-in area, you're less creative. Because the avatar is in the box, you're not as creative, or the avatar is outside of the box, you can think outside of the box. So this is this embedded metaphor, right? So, all right, maybe. Maybe not. All right. This is one of my favorites. This made it to the New York Times. I left a comment. You can go find it. Turbulent times, rocky relationships. What they had people do is rate their relationships. And sometimes they sat on a pretty firm chair, and at other times they sat on one end a little bit of a wobble. Not too noticeable, but a little bit of a wobble. And they rated their relationships as less stable when they sat on the less stable piece of furniture. Now, these come out all the time, and so just this week, I happened to read about Nazis by Kraut, a playful application of moral self-licensing. This is from the abstract. It's a real article. All right? The study shows that drinking sauerkraut juice contributes to stronger support of Nazi-esque right-wing ideology than drinking either nothing or less healthy beverages. And then here's another one. Individual differences in bitter taste preferences are associated with antisocial personality traits. I haven't read it yet, but I did read what Kate Bratzlier, it came out yesterday, said in the Huffington Post. She says people who order black coffee are more likely to be psychopaths. Now, this hits close to home for me. All right. These studies could be correct. They're based on the scientific method. All I'm saying is the claims might be shaky. Now, one of the most interesting quotes, it wasn't really about these studies, but it was about a class of studies that are similar, come from the Nobel Prize winner Daniel Kahneman in his book, Thinking Fast and Slow. And he writes this: when I describe priming studies to audiences, the reaction is often disbelief. The idea you should focus on, however, is that disbelief is not an option. These results are not made up, nor are they statistical flukes. You have no choice but to accept that the major conclusions of these studies are true. So Kahneman is taking the really strong line that our methods work, right? Hey, they did everything right. Clearly, you got no choice. I got a problem with this quote and this sentiment. Let's take another angle. Let's look at replication and reproduction. All right? So this is Brian Nosek, and Brian's been doing this bang-up job of getting people to run other people's experiments. He's been the ringleader of kind of assigning them out and seeing what happens. All right? So what came out in Science, what is this, about 6 weeks ago, was their final results of choosing randomly 100 studies and replicating them to high power, 90% power. All right? And so you'd expect, 90 out of 100 to replicate. That's what the power's for. All right, so here's the original studies. These are the p-values right here. They're all nice and small, below 0.05. Here's the 100 replication, so this is the upper quantile. There's the median, so the median p-value's up here, and 40% are below. This is like the lower between 25% and 50, and then down here is the lowest 25%. But you can see the p-values are much higher in replication than the original studies. All right? Here are the effect sizes. So the effects tended to be from 0 up to 0.75. They centered around 0.3. That was an average effect. But replication effect was about a third as much, 0.1, and lots, 25%, went below 0, and so forth. All right? Here's probably the table that makes it the clearest. They divided it up into cognitive and social. They had 42 experiments that they replicated in cognitive, randomly chosen. 21 replicated out of 42. So of the literatures in cognitive, about a half are true. That kind of stinks. Gets worse for social, where it's a quarter. So 1 in 4 they were able to replicate. High-powered replication failed 3 out of 4 times in social. And this, this is, right? This is a crisis. They also take a look at a few studies where they asked 30 different labs to run them. So instead of doing 100 studies and every lab runs one or parts, right? They actually did the same experiment 30 different times, all right? So the first line is the Stroop effect, and that's a well-known cognitive effect, and all the labs got a good Stroop and nice and tight. And then these are various findings in the literature. The green is the original effect size. The points here are the replications, that's the mean, and the CIs around that mean. And you can see lots of them you have no evidence for. And if you say, what's kind of the factor of attenuation? It's about 10 to 1. Effects are 10 times smaller in replication in this study. Right? I mean, this is just a crazy. This is the original, nobody got it. This is the original, nobody got it. This is the original, nobody got it. What a crisis. And then we got fraud. And so each one of these individuals, Stoppel, Hauser, Smistras, Ruggiero, and so on, has been caught fabricating data and has admitted it in one way or another. And that's a lot for a field our size. I mean, we have a big field, but still. All right? Now, my own thought is that these 3 things go together. Shaky claims, the irreproducibility, and the fraud. They come about from the same dynamics and mechanisms, all right? And they point to a crisis in the production and evaluation of knowledge. And there are some possible causes. The incentives are for quantity. Lots of young people know this, right? They're for beans. We count, right? And so, you got to get those p-values less than 0.05 to get those beans. I think there's not a lot of theory to check against. We kind of make up theory on the fly. It's a little verbal. It's not offering the constraint for bad results that one would like. Whereas in physics, you get a result like cold fusion in the 1980s, and the theory kind of raised the suspicion about it. It didn't make sense theoretically. And I'm going to argue that our very basic statistical paradigm for constructing and producing knowledge is wrong. It's off. And I'm going to argue for a different one, that we have fundamental difficulties and we can do better. And that's what I'm going to talk about today. I'm not going to talk about incentives. I'm not going to talk about theory. I just want to talk about statistics. How do we learn from our data? Probably the most important thing we do. All right. This is a quote from a colleague of mine on how she happens to learn. All right. She says, and this is like before she took my courses, right? And so she had a PhD at the time. All right. She says, I hit the button and I look and hope for red. Statistica colors all p-values less than 0.05 as red. The others are colored black. Red is good. It means we can publish that. So that's a p less than 0.05 rule. Look for red in Statistica. And most of my colleagues would say it works well in practice. All right, Jeff, there are some things around the edge that you statistician types care about, but give me a break. I know, it kind of works. It keeps spurious findings out of the literature. Really? Right? Yes, we could say that, but where's the evidence for that one? And then other folks say, look, it's a standard, right? We like to teach it. We can teach something, right? And everyone knows it. It's a standard. All right, these are true. And so then folks who think about the crisis don't really point to the statistics as being problematic. They say we're prone to bad practices. We do things like censor data. We have optional stopping. Well, we don't like the results. We'll get some more data. We do, we'll stop, right? We'll ignore our pilots. We'll report the 3 experiments that work and hide the 4 that didn't, right? I'm not going to take a big stand pro bad practices. These are bad practices, all right? We even have good names for them now, like QRPs and p-hacking and harking. So there's a whole industry about this now, all right? And the solution is be good, right? Just like ET, right? Don't do things you know you're not supposed to do, right? All right, be good. So we have some good things. We have pre-registration now. Tell us what you're going to do before you do it. It's kind of like being a grad student, right? You got to take your master's and propose it first. That's like pre-registering it. Or take your PhD and propose it. I guess that's what we're all doing. We have an increased focus on open data, and I have an increased focus in my lab right now. Any data we write, it's up in 24 hours, publicly available, free, right? It just goes up automatically. Nobody could say no. The pilots, the burnt subjects, everything. And there's an increased focus now on replication by some of the data I showed you. And there's also something I don't like. There's an increased focus on shaming researchers who are not being good. And I felt a little bad even putting up the authors of those studies. That's why I didn't read it. I don't think this is helpful. I think we're polarizing the field into people telling me, well, you reformers, just go do some real research. All you're trying to do is make a buck or make your academic hay out of telling us what to do. All right. Let's talk about significance testing. This is what we do. P-values, right? So I used to teach methods, so to undergrads, right? And I would teach them, I would start with logic, sentential logic, real simple stuff, like if A, then B, all right? Which means if proposition is A is true, then B has to be true. You could also, for example, if Jane is a US senator, then Jane is an American. If we know A, we know B, right? Proposition A implies Proposition B. Another way of saying it, Jane is a US senator implies Jane is an American. And so we go over all the ways you can do this and what it means and one way and the other way and the whole bit, and we have a lot of fun for a week. And then the next week, we learn modus tollens. If A, then B holds, well, then you could say if not B, then not A. And that's certainly a sentential truism. So if the original statement, if Jane is a US senator, that Jane is an American, you could also say equivalently, if Jane is not an American, then Jane is not a US senator. This is true. Right? You got to be an American citizen to be a US senator. All right, so we go through this. If not B, then not A. Perfectly good logical construction. And then we trot out Sir Karl. Right? Everyone loves to talk about Sir Karl Popper and falsification, the foundations of science. Here we go, research methods, right? And so we teach a premise. If hypothesis H is true, then event X will occur. We add another premise. Event X did not occur. We use our modus tollens, and we come up with hypothesis H is not true. We've falsified it. And so this is what we teach our students. This is how science works, right? And this is the version we actually should teach, and we do. If hypothesis H is true, then event X will not occur. There's some event X that if it occurs, it precludes the hypothesis. Like the magnetic monopole would really make us, all magnets have north and south. If you found one with just north and no south, you got to rethink the whole theory of magnetism, all right? That's called the monopole, right? It doesn't exist. It's a unicorn. If hypothesis H is true, then event X will not occur. If event X has occurred, then we can be sure hypothesis H is not true. Right? We trot this out. Sir Karl, yee-haw, is what we do. And then we make it significance testing, and we do this. We say, if hypothesis H is true, then event X is unlikely. It's rare. Could happen, but not very often. Oh my gosh, event X has occurred. What can we conclude? Well, we conclude that hypothesis H is probably not true. And this is your p-value. This is exactly what it is. Under the null hypothesis, you observe some data that are rare. Data, more extreme, are so rare they occur less than 5% of the time. Throw away hypothesis H. Reject it. Except this makes no sense. It's logically a false set. And if something's false, all I need is one counterexample. So let me give you the one, and then you'll know it's logically false. If Jane is an American, then it will be unlikely that she is a US senator. That is a true statement, right? Most Americans are not senators, right? So that fits the first part of it. Whoa, I've observed Jane is a US senator. Very small p-value. So then by the logic of significance testing, I must accept the conclusion that Jane is probably not an American, which makes no sense. Right? So you can't just take sentential binary logic and put it into the probabilistic framework. It doesn't work. What you need are alternative hypotheses. So if you're going to play the probability game, our data occur with noise, you need some alternatives, real alternatives. So here's an alternative. Jane is not an American. And what I can do is I can figure out the probability Jane is a senator, given that she's an American. And I just said, well, there are 100 senators and 300 million Americans, and that's the probability, not knowing anything else about Jane. Okay? And I also can figure out the probability that Jane is a senator, given that Jane's not an American, and that is 0. And this number, even though it's incredibly small, is infinitely more probable than 0. And so once I form the right ratio, I know if Jane's a senator, then she's an American. Right? I get the right conclusion. Right? And that's the point, is that we need alternatives in probabilistic environments. I love this XKCD. All right? XKCD is one of my favorite, all right? And I hope folks are familiar with it. If not, just go look it up. It's such a beautiful comic strip. All right, so did the sun just explode? It's night. We're on the dark side. The sun could have exploded. We have a neutrino detector, right? And what the neutrino detector does is it rolls 2 dice. And if they both come up 6, it lies. If any other, it tells the truth. So most of the time, if the sun exploded, it'll say yes, and if it didn't, it'll say no. But every once in a while, it rolls a dice, it lies. It says the opposite. All right, let's try it. Has the sun gone supernova? Did it explode, right? Roll, roll, ching, 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 ching. Yes. So the frequentist, that's us, the regular old statistician, goes, the probability of this result happening by chance under the null is 1 in 36. Well, that's below 0.05. So since p is less than 0.05, I conclude the sun has just exploded. The Bayesian statistician, who considers alternatives, says, I'll bet you $50. So one event is a lot more rare than the other, right? Now, the last dig I want to make at significance test is a true human tragedy. It's the tragedy of Sally Clark, the only person I know that has been directly killed by a p-value. Her first child died, and it was ruled a SIDS death. And when the second child died, they arrested her for murder in 1998. She was convicted and then released later. The prosecutor computed that there was a 1 in 73 million chance of 2 SIDS deaths. He said each SID death is about a 1 in 8,000. He just multiplied them, never mind genetics and what have you. But let's just take the prosecutor's numbers for right now. All right? 1 in 73 million. Went to the jury, said 1 in 73 million. It was SIDS, as she says. You have to convict. All right? And they did. So here's the logic. 2 SIDS deaths are so rare that it must be murder. There's a p-value, 1 in 73. It's a probability of this happening under a null, 2 SIDS deaths. What's the probability of the data, right? It's just too small, right? And so she was convicted by this p-value in 1999, and the British statistical community went a little berserk, and there were lots of articles and public pressure, and they finally reversed the conviction, which I doubt they would have done in the US, in 2006, and she was released. Right? But her life was ruined. Her husband in the report says she was never the same. She was a shell of a person. And in 2007, she died by acute alcohol poisoning, probably suicide. The complete tragedy of losing your children, of being falsely convicted, imprisoned, and the like. So the prosecutor's logics were 2 SIDS deaths must be so rare that it must be murder. Well, we could reverse the logic, right? How rare is murder by moms? How many moms kill their kids, right? It could be even more rare, right? Suppose I said murder by moms is the null. To have 2 deaths by murder, well, that doesn't happen. It must be SIDS. Right? And what you really need, now I'm not saying you can't know, what you really need to know is what's the relative probability of murder by mom, what's the relative probability of SIDS, conditional on 2 deaths. That's what you know. And you have to compute these as the way we should be doing it. This makes sense. But this is not significance testing. This is not what we do in psychological science. It's not what we do in behavioral science. We don't propose alternatives. We keep one hypothesis, and in the course of doing so, we always overstate the evidence against it. All right. So I'll just quote myself. I have this master's in anthropology, and I just have the opportunity to write with flourish, and if I'm going to be bombastic, why not? Significance testing has reduced data analysis to a series of prescribed procedures and fixed decision rules. We use the 0.05 rule to reify results without appreciation of subtlety or qualification, and to manufacture a consensus even when this consensus is unwarranted or meaningless. It is in this space where significance testing is simultaneously a bureaucratic barrier and a sanctioned ritual of truth that we take our shortcuts, be they minor infelicities at the gray borderland or major failures of outright fraud. I think the way we treat statistics, that it's objective, cut and dry, we got to get there, is driving the bad practices. And I think it's driving the irreproducibility and the shaky claims and the fraud. So I'd just like to take this opportunity to tell you about my statistics. For me, statistics is about adding value. I think objectivity is a myth. The concept of truth is not particularly helpful. And when we do statistics, it should reflect our beliefs, our judgments, our insights, and our creativity. Kind of like everything else we do in science, right? That's how we do science. It reflects our insights, our judiciousness, our values, our beliefs. And so should our statistics. It's not this refuge, it's not this island of difference. Readers should be evaluating the judiciousness of the value-added components. Does that make sense? So I'd like to put this in motion with 6 principles. So the first principle is, what's a model? A model takes a theory on one hand and data on the other hand, and it connects them. It connects theory to data. So let's take some theoretical statements. Working memory training transfer. This is kind of, you practice one task, working memory, and your memory improves, like luminosity, right? And so the idea is you get smarter, right? Practicing one working memory task will increase performance in other related tasks. That's a theoretical statement. Stereotype activation. People will identify weapons faster following African American face primes than following white face primes. Statement of a theory about automatic activation of stereotypes. Weber's law is in perception. The amount of energy you need to add to a brightness to get it to be detected is proportional to the background luminance, right? Just a little mathematical law. Still math, right? But it's a theoretical statement. Or maybe one, eating ice cream diets leads to weight loss. All right, that's my diet. I would say each of these statements describes a constraint about the real world, right? And yet none of these may be tested with data. These statements are not in the form to be testable yet, right? And that's because none has specification of sampling noise or errors in measurement or anything alike. None really make predictions. They're just words at this point. All right? They describe constraint in data, but it's not quite there. All right? And that's appropriate. That's the level at which theory should be. We shouldn't be changing theories. All right? Models are those things that go in between. They instantiate the theory and they predict data. So models lead to statements about observables. The probability that an observation will be in this interval or that interval is this value or that value. All right? That's what a model does. And if you take this, actually, you're already Bayesian. But I'm not going to get into it. Models are proxies that capture constraint in theories. What we learn about the models, we then apply to the theory, right? They're kind of the proxies in between. So that means model specification is necessary, and it's always subjective. It always reflects our beliefs on what we expect is reasonable about data, right? And so we're always modeling. And if you want to use theory with data. You got theory, you got data, and you want to put them together, you're a modeler. People tell me, oh, I'm not a modeler. That's for you guys, right? I just do the experiments. Or I just, you're a modeler. Sorry. You're doing it, right? The question is, are you going to do it explicitly, know it, own it, and understand it, and use it to your benefit, or are you going to follow some outdated textbook recipe? All right. Principle number 2. Models are neither true nor false. Let's get rid of this idea of a falseness or the truth of models. Now, George Box once said, all models are false, but some models are more useful than others. Turns out Box got it wrong. He should have said, models don't have truth values. Some models are more useful than others. Or I think his dictum would even be better if he just said, some models are more useful than others. Right? The truth and false is not that important. This is a map, a metro map of DC. Is it true? Is it false? It's a map. And so when people say, is a model true or false, I say, it's a model. And there are some things about this map that capture the important constraint, right? So the map in the data, in the real world, the ordering of the stations and the intersections of the line, that's the constraint in the real world that's being captured and instantiated here, right? There's some things about these maps that don't exist in the real world, right? The colors. You go look at the tracks. I've been there. They're not that vivid yellow. They're not that vivid orange. They're not that red. If you say, is this false? Yeah, the colors are wrong. It's false. They're all steel gray. That would make this less useful. All right? That's what models do. They capture the important constraints. They fudge the ones that's not to make it useful. That's how, and they're not true or false. They're maps. Now, this would be a particularly bad map if it had the stations mislabeled. It wouldn't be very useful. True, false, it's still a map. I don't know. All right? So, if you believe that models are neither true nor false, what you really want to do is compare them. Right? Because they're all going to miscapture something about the data and get some of the important constraints right. And that's what you want to know. How much of the important constraints does it get right? Right? You take a theory as a model and it places constraint on data. Now, you need a meaningful alternative. You need another model that instantiates alternative constraint. You say, this is the important constraint. Here's a model that has a different set of constraints on the data that contrast to this in a way that makes sense to me in my subjective world, that will highlight it. Right? So for the map case, the important constraints is the labeling, the order of the stops. I would have a map that has the same colors and different orderings and different. That way I can compare them. All right? And so we want to know the relative evidence for the target model against the alternative. We need 2, at least 2. All right? Now, the specifications of alternatives is strictly necessary. I can't do principled inference without it. I need alternatives, real alternatives. And if you agree with me, these alternatives require substantive knowledge, not statistical knowledge. You need to know something about subways and stops and the like. All right? And so then the models become the responsibility of the substantive people rather than the statistical analysts. We've kind of deferred that. We said, give us a model. It's our job. All right, principle 3. So two so far. Models go between theory and data. Models are neither true nor false. Evidence comes from predictions. Predictions really matter. If I have 2 competing predictions about data from 2 competing models, then I'll just collect the data and wait and see which one predicts the data better. It's really simple. Which one predicted it better? Just that easy. 8-year-olds get it. But we tend not to do this. We don't really make predictions, not in a way that is helpful. Now, when I say predictions, I mean before I get the data. Some people say, oh, I predict it's at the sample mean. That's after you get the data. All right? So predictions means you got to say where's the probability the data lie before the data come in. Right? Not post-diction. All right. So the usual null model. I have a mean is 0, let's say. So change in weight of eating ice cream has no effect on your weight. Mu is 0. this model actually makes predictions. You can say something like the t-value is usually small. It's a null model. It's usually between -2 and +2, right? I could put a probability on that interval, or any interval I choose, right? So I can talk about the probability of where the t is going to lie, right? That's a prediction, okay? But the alternative model, mu does not equal 0, or mu is greater than 0, or mu is less than 0, there's no prediction there, folks. We talk about this as a hypothesis, but we're saying nothing. And if there's no prediction, you can't put probabilities where the t is going to be, right? You don't know if it's going to be 5 or 50, right? And if there's no predictions, there's no relative model comparison, and for me, there's no principled inference. Prediction is still the key. So the solution is to specify alternatives that make predictions, and this takes substantive knowledge. And it's subjective, and it's the value you add. That's your beliefs. So let's do an ice cream diet. What do you guys say? So the data are x1 to xn, weight changes 1 month for n people on the diet. I give people ice cream every night for a month. Weigh them before, weigh them after. Take the difference score, that's my data. All right, it's a little experiment. And so I have some x bar is like how much on average did they lose or gain. S is the variability, right? And mean standard deviation. And the observed effect size is the change relative to the standard deviation, right? Standardized unit. Right? And let's place some competing models on the true effect size delta, all right? Just to see what happens. So here's my first model, model not. It's all, nothing happens, null. This is the null model. All of delta, delta is OE 0. And I put a spike there to indicate delta is OE 0. It has no variability. All the density is there. And it makes a prediction about observed effect size for some sample size n that looks something like this. It's not too big, it's around 0, it's spread out because there's noise, right? So this is the true value of the effect size, that's the sample value, a little noisier, okay? Well, here's another model. Well, there might be some change, right? But it's most likely null, and so smaller changes are more likely than bigger changes, right? And we have a belief that we're not committed to weight gain or weight loss. We're not sure. We're saying weight gain and weight loss are both equally likely. All right? And so there's our model. And then when we add in the sample noise, there's our predictions. And we could literally say, what's the probability of an observed effect size between 1 and 2 on both models? Or what's the probability of an effect size at 0.5 for both models? Right? And so then we go and we do the experiment and we get our sample effect size. All right? So let's take the case that the sample effect size is small, 0.2. This is at 0.2 right here. All right? And this black dot is how likely it is under model not, the prediction, and this one's under model A, the alternative, and this is 3 to 1. And now we've learned something. We have 3 to 1 evidence in favor of the null model. All right? Alternatively, if the data is out here, the effect size came in, it's 0.5, right? Well, this is about 2 to 1 in favor of the alternative. So once we specify the alternative so that we can get predictions, it's just a matter of conditioning on the data we get. What's the probability of this data given one model? What's the probability of this data given the other model? Figure out the ratio. That's called the Bayes factor. It's a measure of strength of evidence, completely principled, tells you how to change your beliefs about data, calibrated, and beautiful. Evidence, relative prediction ratios. So for the small effect at 0.2, we would say we have 3 to 1 evidence of the null over the alternative. For the larger effect of 0.5, we have 1.7 to 1 evidence for the alternative over the null, right? Whatever the sample effect size is, we can make these calibrated statements relative to our beliefs about what the alternative and what the null is. All right, my fourth principle, state evidence. Avoid decisions. You have the number, state it. Quick, is that a criterial number of bananas? Right? Is that a lot of bananas? 3? Is 3 a lot of bananas? Well, 3 is half as many as 6. Twice as many as 1.5, right? We know what it is. We don't have to say whether it's a lot or not, right? It depends, right? So there's a little hamster eating a banana. 3 would kill this poor little guy. right? There's a football team. You want to give them 3 bananas at halftime, you're going to get a fight, right? For the 3. Okay, 3's not a lot here. It's way too much there. This is how I think of these evidence ratios, all right? They're like bananas. You get an amount, you know what they are. 10's bigger than 5. They're like horse racing odds. Is a 5-to-1 a prohibitive favorite? Depends. What's the context, right? We should be like Fox. When we publish, we report, you guys decide as the readers. You have to bring your value and your subjectivity too to understand the literature. All right, now, I think it's a great tagline. I'm not saying Fox does it all the time. They could do better maybe. There are other taglines for Fox. All right, so we add value. That's what we do as researchers. In the current zeitgeist, statistics stands apart. Statisticians are a scary bunch. Most people would like to tell you statistics is objective rather than subjective, especially ones that don't know it well. Most would say it's the domain of specialists, and I sometimes tell my lab I'm going to visit the priests in statistics. I have a question, right? My priests are Dong Chu and Paul, very high priests indeed. Statistics is governed by rules and procedures and fixed things you have to do. Geisler greenhouse corrections and sphericity and all sorts of things, rather than governed by, say, creativity and insight, right? How creative is it to compute a t-value, right? You just got to remember the formula. And for some people, statistics is hard and scary. And what happens is statistics stands apart. It's separate, it's different, it's otherly, it's alien. We don't take responsibility for it. We don't own it. Could be good. I like being respected. People come in, and have a lot, or Paul, all of us like being respected. We're placed on a pedestal. Right? Really, most folks just patronize the hell out of us. They just say, just tell me what to do. Right? Oh, for Pete's sake, enough of this Bayesian stuff. Just tell me what to do already. The real dark side is it's really data laundering, right? Here's my data. Make it kosher so I could publish it. It's like you got the drugs, you need the money. I got the data, I need the pubs, right? Same process, it feels like. And the ugly, it's a true, the way psychologists think about statistics, in my mind, is a true abrogation of intellectual responsibility. They're just not willing to say, what do I really need to do to know? I don't want to farm this out by consensus or by consent. So please, 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 take us statisticians and knock us off our pedestal, right? I feel like a 1950s woman there, you put them on a pedestal just to keep them from being part and taking part on an equal basis. Let's have a little bit more equality when we interact, right? Treat statistics like all other parts of the research endeavor. It is no different than rhetoric. It is rhetoric. It's creative, it's insightful, judicious, theoretically motivated, subjective, and varied. We can come to different answers for the same problem and all be fairly right, or all be fairly judicious, or all represent the structure as we see it in data. Add value. Where? In the models you choose to instantiate theory, in the models you choose to instantiate alternatives, which are needed, in the evaluation of those bananas, the meaning of evidence, those ratios. How? Based on substantive expertise and domain-specific knowledge. You know a ton. You know where the effects are going to be if they're there. Don't be afraid of that. Be subjective. You have informed opinion. It needs to be there. And don't ask your local statistician. What happens is that they end up learning the substantive stuff and then they become substantive researchers with you. They stopped acting like statisticians at that point. They just don't know it. All right. So let's take 3 teams or 4 teams that might choose to add value differently. And let's just see what happens. All right? So this is Team A, and they have a null model here, and the alternative like this, and there's their results. And we went over these. There's the 3-to-1. There's the 2-to-1 the other way. You guys see that? All right. Here's a different team. Team B said, geez, for the effect I'm studying, if I look at the literature, I tend to find, this is a really bad laser pointer. I tend to find effects that are moderate in size. I'm going to, just for the sake of exploration, say both sides are equally likely, all right? But really, they're moderate. That's what we tend to find in literature. Everyone can get these effects if it holds in this case, right? If it's like those other ones in different variation, maybe I should expect this kind of bump and hump here. And here are the predictions smeared out by sample noise, right? And then you form the ratios. And now they're going to say for the 0.2, it's 4 to 1 for the null rather than 3 to 1. All right, 4 bananas. And they're going to say it's like 2.2 to 1 against for the bigger effect, right? This gave them more focus. The hypotheses are more dissimilar, so they had more resolution, right? Okay, I can deal with that. Here's another team. Now, what happens on this team is that most of the members feel the hypothesis is going one way, right? MP. They say it should be one-sided, all right? And then there's this one graduate student who says, no, 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 you guys got it all wrong. The way it works is exactly opposite. So we decided to keep all 3 models. They're all motivated by theory about what somebody believes is going to go on, right? So there's the negative going model, the null model, the positive going model. Now I have 3 dots. It's 3 to 1 going up and 5 to 1 or 10 to 1 going down, right? And so we know the null model isn't working, and here it's even worse, right? And so that's okay. We can carry one-sided models. We could have conflicting models. We can carry multiple models. There's no, as long as you have a theory for them, and they're an interesting point of view that's theoretically motivated, that makes constraint on data, do it. And then go report your numbers. You report. We'll know what the bananas mean. Oh, Team D, they cheated. They ran the experiment and put the alternative where it was, right? Or they said, I'm just going to have 1 point as an alternative. In this case, it was right where the data were for the first experiment. All right? And so they have different results. It turns out the null is not supported, right? Because if you're free to look at the data, the one you pick will always be the best, right? And so, they just kind of made it up as they went along. This is injudicious, right? So here's the evidence for all 3 teams. For the small effect, 3 to 1 for the null, and 1 to 2 or 1 to 1.7 for the large. Well, let's do it this way. For the small effect, 3 to 1, 4 to 1, 2 to 1. That's for the best alternative, the null relative to the best alternative. And then Team D got the other result, 1 to 1.5. All right? And then for the big effect, 1 to 2, 1 to 2 and a bit, 1 to 4. All right? And this one's a little higher. Okay? I would say because these 3 are making good faith attempts and have theories behind before, yeah. And then Team D, we could see through that. That alternative was too perfect. It was right at the point, right? You could say, why'd you choose that alternative, right? So readers add value. With conventional statistics, readers are along for the ride. You just have to listen to Daniel Kahneman. Disbelief is not an option. With my statistics, I'm adding value subjectively. You're not along for the ride. You add value. You add value the way you read my article, right? And this is what we really do, right? We do add value when we read. We do reach judgments. We do have opinions, right? We're not along for the ride. Disbelief is always an option, right? Kahneman is just wrong. Let's make it part of what we do, though. Let's make it part of the culture of what we do. Readers have to evaluate the judiciousness of the value. Does that value make sense? Do those models make sense? Do those predictions make sense? They form their own meaning of the evidence, and they should embrace some diversity. If we're going to be subjective, we need to embrace diversity. There's no one right answer. We know this. Let's just make it part of the statistics. So if I was the reader, I would take all the variation that's in Team A, B, and C, and I would reject Team D. I would say, for example, for 0.2, the evidence modestly favors the null. Body weight is invariant across the duration of the study. And for 0.5, if we'd observed that, I'd say there's some tentative evidence from teams A and B, and maybe and very modest evidence from C. And because the evidence is fairly tentative, 3 to 1, 4 to 1, in other words, when you say my evidence is 3 to 1, you're telling a journal editor, well, If I'm wrong, I'll pay you $1. If I'm right, I'll pay you $3, right? And is that really a bet a journal editor wants to make, right? Maybe it's a little, maybe you should have more money where your mouth is. And so I'd like to see for a study like this, bigger sample sizes and better evidence. All right, 6 principles at once. 1, models connect theory to data. 2, models are neither true nor false. Make relative comparisons. Evidence from predictions. State the evidence. Add the value. Knock those statisticians off their pedestal. And as a reader, read to add value. Read critically. Read judiciously. All right. So there are critiques of this. And so one of the claims is it's all too subjective. Here's my Heisenberg uncertainty principle. I don't know. You can go back to Sally Clark if you wish. You can go back to the irreproducibility of psychological results. You can go and say, well, they did a p-value, those shaky claims got to be true, right? It's not too subjective. That's a myth. There are limits to what we can know. We have to pay to play. We have to add our value to learn from the data. If we want to understand structure and data, we have to bring our beliefs, to bring our biases, we have to bring our opinions. We have to do it fairly and judiciously. We have to be open to others. We have to accept diversity and do that to understand structure and data. It's not a pretty answer, but statistics is hard. Science is hard. All right, some people say, I don't know how to specify these alternatives. Yeah, you do. Let me give you some examples. Suppose these are in effect size units. Would you be happy with this distribution of possible effect sizes? With real mass, say between 20 and 40? Have you ever seen an effect size of 20? 6 is effectively a light bulb going from on to off in voltage. Right? You don't need much mass out past 6. I guarantee you, right? This is just way too... You're saying ahead of time, I expect huge effects. That's too spread for most any scientific endeavor, unless you want to drop paper airplanes and pennies off the new Freedom Tower. This would be appropriate for that, if your data were that clean. How about this? It's too narrow. There's no mass out at 0.3, at 0.5. This is where effects live, 0.8, right? This is too narrow, right? It's too much like the null. It's not a good model for effect sizes that we look at in psychology. All right? So here's one that's wider, and I'd say this is kind of for big effects that you expect, maybe effects of people or some big subject variable, aging, or something, right? You know. And then this one's a little narrower, maybe social priming or something. You could tune these. You know, I don't mind it. But I take data, your belief. If you said, this is my belief before I begin, I'm down. If you said, this is my belief before I begin, I'm down, right? You got a different shape, I'm down. It's your belief. You know, you're going to argue for it by recourse to literature, similar studies, what we know, what we think should make sense theoretically, the size of effects. You're going to use your knowledge. And the more of your knowledge you use, the more persuasive it is. This is the Bayes factor, those evidence ratios. And what I want to say is, it doesn't matter that much. It matters far less than you might think. This is the t-value, 0, 3, and 5. The red is the impossibly small setting. The other red is the impossibly large setting. The green was kind of my narrowest. This green was my widest. The middle two I showed you that I'd accept as kind of a range. The Bayes factor really doesn't vary that much across all this change, the evidence ratio. It's not that sensitive. Sensitive matters. It doesn't really change things by more than a factor of 2. Take your bananas as fuzzy, times 2, right? If I say 2, it might be 4, it might be 1, that's reasonable variation. But if I say 4,000, right, it's not 2, right? And that's the idea for me, is that I'm willing to allow diversity in these numbers. I know they reflect beliefs, it's subjective, but not so much. Not an order of magnitude, not even a factor of 5. Factor of 2 at most. All right. Now here's the thing that people tell me all the time. Jeff, what will the reviewers say? And let me tell you what I should tell you to be nice and kind and a get-along guy in the field. I should tell you some reviewers may applaud your usage. Some reviewers really like it. They say, that's innovative, right? Others say, oh, they're just hiding with that Bayesian stuff. I never believed the result, now I doubly don't believe it. When they're critiquing the Bayes factor, there's a proxy for something else. It's not like this is a great study except for the Bayes factor. I've never seen that, right? This study stinks for this reason, this reason, this reason, and the Bayes factor, right? It's usually a proxy. It's just they're thrown in the kitchen sink. It's part of the usual the reviewer verbal diarrhea that you get. Now, if you have a good paper, and you might want to take this as a teachable moment. I do. Sometimes I do it snarky. I put p-values in upside down or something, right? But if you really want to know, turn the journal around, right? This is a teachable moment. You can teach people in your letter, in the text, in your footnote, what's going on. Do some field service, and that's nice. I think if you do this, there's some real nice long-term upside, especially for young people. You're going to be an early adopter of the way things are going. Bayesian is like silicon. It's the future. Long-term upside is you're going to be viewed as independent and innovative. What I want to tell you, though, what I really want to say whenever I see the reviews, right? And really, I hardly ever get this anymore. But if you got a review and said, Jeff, look, I did this Bayes factor stuff. You taught me how to do it, and look what happened, right? I'd say something like this, and you wouldn't like it. But I'd say, what the reviewers say, or what they might say, is really irrelevant. You and I have this unfathomable privilege of being academic scientists. To honor it, you and I have the obligation to act with the utmost intellectual integrity as we individually see it. I'm not telling you what the integrity is, all right? But for me, I know what it is. I can't use p less than 0.05. It's dead to me. It doesn't make sense. It's always overstating the evidence against the null. The null's a straw man, all right? It's dead to me. I have no choice. My hands are tied. This is my integrity. And if you come along and join the ride, you might feel the same also. But whichever way you do, don't forget about this privilege we have as being academic scientists. Thank you. Sure. And I don't have my glasses on, I'm sorry. It is Laura, okay. I thought so.
How can we get this message across? What can we do? Do we just do these Bayes analyses and show rather than tell?
I think when you're adding value and finding these alternatives, people are going to find them compelling and interesting and an area of intellectual exploration that's not in the other paradigm. So there may just be a constructive idea. I just want to know to folks who have this null hypothesis testing what this is about, right? Unless you think Brian made this up, and he didn't. How do you explain this? I think what I'm trying to say is you're trying to get something for free that you can't have for free. You can't do inference without paying the price of specifying that alternative to some detail. It's just logically not right. just by those logical examples, right? People are I mean, it's hard to tell people something's wrong when their living depends on it. It really is, right? I mean, so I just focus on the young people. And I do. I think it's great that that editor has that response. I want to know what that editor's student is going to think. That's really what I think the answer is in the young people. We all have frequentist DNA. We were all trained as frequentist p-value statisticians. All of us, right? We all rely on it. It makes sense. It's been naturalized in us, all right? But just because it's natural, like we have certain theories about motherhood that seem natural, but they're just constructions or what have you. They're just constructions. It's really hard because we're so comfortable with it. It's almost like a sociological phenomena more than an intellectual one, right? It's, you just can't excise this DNA. It's there in the background, always saying, condition on truth, right? Control long-term error rates, right? They're like ghosts in your head. I get it. It took me 10 years and this is not real rocket science, right? I don't know what to say. It's just a process. Go ahead, Laura. You just looked so unhappy. You look so unhappy during my talk.
I was the same conference, Laura, and
All right.
I just thought, my own feeling is, there's what else has to happen for people to notice that things aren't going that well. We published a paper proving EMT, the top journal in our field, our research is completely unethical, and we continue to provide by outright monsters. What has to happen for people to be shaken loose from not only posture significance testing? I don't know if you know that the editor of Basic and Applied Social Psychology outlawed film and posture significance testing. And so he was in the same session that Laura attended. He gave his talk about why he outlawed an HSP, and it was essentially the exact same logic that you gave. And people just were like, la 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 la. And I guess one of the things I thought of as he was talking and as you've been talking is that these aren't the ways we think about data. And not me, because I think about data that way, but other people don't. And what I mean by that is, correlational researchers, it is not problematic for me to think in terms of an effect size and where I think it's going to be. But my friends, many dear friends who are experimental social psychologists, don't think in terms of effect sizes at all. They think in terms of, here's what you mean, this one's going to be bigger than that one. Or here's what, they do not, they think about life in a 2x2 table of bar graphs. And so maybe there's something about continuous themes that offer. Talking about it in this way is much less meaningful to them than if you talk about it. I guess what I'm trying to do is please help me by talking about it in that way. Can you talk about it? I asked David Kaffenroth, can you tell me what you would do if you wanted to say, without using NHSP, about, like, I'm going to compare to the mean? Because his view is you don't need non-health testing if you decide what power do you need to show this. You do that in advance. If the difference comes out, it is what it is. It's real. So you couldn't really show us how to do that now.
Let's talk about it later on, because I'm not sure I understand. You're asking me almost a rhetorical, like what's the best rhetoric, right? What's the best? And God, I wish E.J. Wagenmakers was here. He's our minister of propaganda in the group. I mean, you'd think I would be, right? But E.J. really is slick. He understands everybody and everything. I just like to shout. So let me put that one on hold. I don't know how to tell. I know what I think and what I believe, and it makes sense to me, and I feel like I have a coherent set of principles that can improve psychological science, but they require thought. I'm saying it's a thinking person's game. You can't just do it by algorithm alone. Nelson.
Yeah, well, you said you had to call on the other people.
Yeah.
Anyway, I think everything you have said, your line of reasoning makes a lot of sense. But human nature being what it is, I don't think I
I agree. The 3-to-1 is harder than the 0.05. It just takes a bigger p, and the more n you get, the even harder it becomes. So it's not like, see, the thing about significance testing is you get a big enough n and the smallest effects pop, right? The Bayes factor has a safeguard against that. All right, so you can't just keep running like 1,700 subjects to get the tiniest effects to pop, which happens, right? And so it's going to make it a little harder. Joe Hilgard, bless his heart, when I remember he came in because I've been playing with this Bayes factor, and you make it harder to show effects. And he goes, it's hard enough as is. I don't need it to be any harder. And Joe does good research, right? And he's doing great, but it's going to be a little big barrier. You're right. If it's just the formula of go to Rouder's website and put in your t-value and get your Bayes factor and see if it's bigger than 3, that's not much of an improvement, right? I hope people use it to add value. EJ and I differ about this. EJ wants people to be Bayesian first and model second. I want people to model first and be Bayesian second, right? I want them to think about what's the distribution of data under different theories before. I think that would be really helpful and protect us. And as readers, I want to do that. Yes?
So I'm used to statistics being characterized as having frequentism, likelihoodism,
Right.
and Bayesianism.
Right.
And Bayes factors, they look like something that likelihoodism could grow with. And so I wonder if there's something beyond Bayes factors that you want to push that makes the approach completely Bayesian, and rather kind of in between positions.
Oh, no. The Bayes factor is completely Bayesian. It's the direct consequence of Bayes' rule of updating.
Right.
It doesn't have the posterior odds, right? So if you want to put in prior odds and then interpret posterior odds, that's how you change, right? And so the posterior odds, some people claim to me, oh, you're only Bayesian if your target is the posterior odds, right? But I think evidence is how beliefs change in light of data, not what beliefs are. So the Bayes factor tells you how to change your beliefs in light of data, not what your beliefs should be. Right?
Attribute the probability of the hypothesis, letting your inference be valued by Bayes factor.
You do. You do when you marginalize, over the parameters, which in effect is the probability of the hypothesis. When you marginalize your likelihood to get those ratios, to get those predictions, you're integrating out all your parameters. And in doing so, you have to put in the priors, at least on parameters, and if they're unbalanced, it would be the same as on hypotheses. Yes, you can go to posterior odds and provide prior odds. Yes, we're not doing that here. That would be the next step if you chose. You can do both. Sometimes I say it this way. The Bayes factors is the evidence from the data. But if I want to provide my readers with context, I might tell them a prior odds that I would hold on the hypotheses and then tell them what the posterior odds are. I don't know if that helps. But remember, it's not a likelihood ratio. It's really different. What you're doing is, in any of these models, you have to integrate out the parameters to get statements of the probability of data. In any frequentist approach, you can't do that. You say the probability of data conditional on a parameter value, something that God knows and I don't, right? In the Bayesian case, you actually can integrate it out. Frequentists don't have probabilities of data. They only have probabilities of data as a function of unknowns. Only Bayesians have probability of data without the unknowns. And that's what this is leveraging. So it's really, truly Bayesian.
Something about the subjectivity you were discussing. So you said that all of the alternatives had pretty much the same Bayes factor. Could you say if anything would be said for the alternative that's favorable to the outcome to remove any level of criticism for the way you selected that?
That's a great idea. Or reporting 2 or 3 models, which we do in our papers. We say this is our informed, our best model. This is the model we think that it's at the range of plausibility in this direction and the range at that way, and here are the Bayes factors. Yeah. No. So for example, Chris Engelhardt has a paper in Psych Science about the effects of video games in typically developing folks and folks with autism, right? Aggressive behavior. And we do that. We have a range of Bayes factors for different choices of alternatives in that one, just to cover the spread. Yeah, it's a good idea, I think. You're not penalized for holding multiple models. There's no, it's not like frequentist where you have to correct. It's the opposite conditioning. There are other cute things you could do, like you could sample, keep track of the Bayes factor, and stop whenever. It doesn't matter, it's the same interpretation. You're allowed to do optional stopping. Yes?
Do you know of any scientific fields where your proposals for doing statistics are actually widely practiced?
Widely? Yeah.
Is it the case that in those fields we see less or greater fewer outlandish?
Well, I think the leaders right now in holding that probably are the theoretical high-energy physicists. Well, they're not theoretical, the high-energy physicists will use Bayes factors or Bayes factor-like computations. Now, they just did the whole Higgs boson in 5 sigma, right, which is not, right? That's a frequentist way of thinking about it. And there was a long discussion why they did that, right? But at 5 sigma, that's a pretty high bar. There are a lot of physicists that will do it. I don't know if it's the majority. I don't read physical letters or physical review that much, except when I see one. There was a wonderful paper in Nature that asked the question, are we all from one common human or from several humans in our lineage? Do we have one single ancestor? That was a Bayes factor, and they concluded one, right? So you see it here and there in various ways. I don't think it's been widely adopted. The statisticians, I would argue, don't adopt it except for a few. And those that do really are interested in frequentist properties of the Bayes factor, which is they're not fully subjective, I would say. They call themselves objective Bayesians. It's a funny use of the term. I don't know. There are a few everywhere, but it's not clear that... Paul, you have any opinion about this? Yeah, except in sometimes in big data, they're being used implicitly. So you have a big data problem, you expand it out, and you put spike and slab priors on your coefficients. You have lots and lots of parameters, and you want to zero them out really quickly. And so you're zeroing them out by Bayes factor and throwing them out of the model. And that's really routine in genetics and consumer research and in weather, and all these big data problems. You have sensors all over the Pacific, and you have these models, and you have to talk about oscillations at different frequencies, and you want to get rid of a bunch of them, or wavelets, different coefficients. How do you null out wavelet coefficients or regression coefficients? That's a Bayes factor computation like this. It's exactly what this is. So it's being done routinely in big data, but not the same inferential gusto that I'm advertising. To me. I probably should not say that.
How long has it stuck around? I mean, I just wonder, why has it gotten more traction by this point than it has? Is that because the apparatus is only around for a decade or so?
So the Bayes' rule comes from Sir Thomas, Reverend Thomas Bayes. I want to say 1789 it was published. What's that? All right, so somewhere at the end of the 17th century. I think he passed away earlier, but I think it finally got presented in 1789. And Bayes understood the implications for subjective probability. Simon Laplace in 1811 talks about odds ratios, the notion of probability of data given hypotheses, and the inverse, right? And so he's the first one to say make these odds ratios and use them. And then it gets hard, Because to do this, you have to integrate out all these parameters. And nobody knows how to do it until about, say, well, Metropolis, you could say, is probably the earliest implementation of real computing integration of this type in pursuing the bomb. He comes up with this algorithm, and it doesn't really catch on until statistics until the 80s, until you have the Gibbs for kids. And so now the computation's in play, the computers are coming up to speed, right? Because it's still numerically calculated, right? And so it's only... Harold Jeffrey sees it all, backwards and forwards, writes a beautiful book, sets the stage. At the same time, Neyman and Fisher are around, and they have their points of view, right? And like I said, everyone's a frequentist DNA, has frequentist DNA. And so it hasn't been readily practical until, say, within the last 30 years. It's only in the last 30 years, 40 years, that it's practical. Right, to some degree. And it's being used a lot. It's just under the surface. It's kind of like Linux. It's in those back servers that are doing all the commerce, right? It's being used a lot, right? You know the book, it's a theory that wouldn't die, right? But you're right, it's not the first choice. And I don't really have an insight into the sociological problem or the issue. I just know it makes sense for me. And just kind of have a little, I'm done being ecumenical about it. I used to be ecumenical. All points of view, good points of view is like being a mystic, right? You could, and now I'm not. I just know this is the principles that work for me. All right.
So, let's think about what Kahneman said, right? So, you don't believe that these things are true, what about the data are, the intelligence that this is the truth? There's a lot of ways in which very important that, or at least useful from the perspective of science, to be able to say that to someone. For example,
Global warming.
No, I'm so glad you told me that, because the scientists told me the same say there's this thing called evolution, but I feel like the world was created in 6 days, and now I know that my belief overcomes that numbers, right? I love this new idea. I can bring my subjective beliefs to bear on science. So I believe that, the races should become separate. These social psychologists tell me that I'm precious. I know it's not good, right? Do you see that maybe what you're planting is a seed that is not good?
Well, I think you could make that point if I said, if you could. So in other words, when you bring these things to bear, your prior beliefs and your subjectivity is so ingrained that it precludes you learning from the data in a certain sense, right? You have the Rush Limbaugh prior, right? And so, yeah. But he does. But the point is that if you're a Bayesian and you're transparent, the rest of the world can see it. It's transparency, right? This is what I think. This is how I'm going to analyze the data. You're doing it anyway, right? Let's just make it transparent. It's almost like it's the right accounting for what you're doing. Don't tell me you guys read these things and you think they're objective, right? We still are only 1 in 4 is true. You got to choose. And, right, you are reading these things for methods, right? Does that method make sense? Does that operationalization make sense? Do they have the theory right? You're doing this already. Why is the analysis so different? You're already doing this. And what you use in your argument and rhetoric to preclude those other elements of being co-opted by the anti-vaxxers and the climate change deniers, you use the same arguments and rhetoric for the analysis. There's just nothing special about it. It's part of the process. It takes part in equal footing. All right, thank you.